Hi, this is Dr. Remenacker. In this video, we are going to look at using what is called the chain rule to compute derivatives of a particular type of function. That type of function of chain rule is applied to is what is called a composite function. Let's first take a minute and refresh our memories on what on earth is a composite function. Going back to algebra classes that you've had, a composite function, as the name implies, remember a composite means made of several things. So this is going to be a function made of several different parts or pieces. A composite function is a function that's made of several different pieces. Let's create a composite function. We got a couple of pieces here. Let's say f of x equals x squared plus 6. G of x equals 3x plus 1. Okay, first, let's get down a notation for a composite function. One of the notations is f of g of x, like what you see here on the left side. A similar notation is f of g of x, where instead of having a second set of parentheses, the notation uses a small letter O. Okay, so sometimes people read that as fog, but actually that's not the letter O, it's just a symbol. Okay. Let's take a look at this first notation. If you'll recall back to when you first started algebra, if you would have had something like f of 3, what that said was look up the function, well, that's x squared plus 6, and every place there's an x, substitute in the value 3. So this would simplify then to give us 15. Using that exact same pattern, we can rewrite this composite function over here, where we are going to put some parentheses with an exponent of 2, leaving that blank inside the parentheses for whatever goes inside, then plus 6. All I've done is I've used this function x squared plus 6, and every place there was an x, I've just put a set of parentheses. Now, according to the notation, inside of those parentheses, we're going to put the function g of x. Well, that means we're going to substitute in 3x plus 1 there, where the x would have been, and square 3x plus 1. When you square the 3x plus 1, you get 9x squared plus 6x plus 1. Remember, this is the result of FOILing. First, outers, inners, and lasts. So that's where the part of the equation inside the parentheses comes from. To the far right-hand side, the plus 6 just comes along. Then at the next step, all I've done is I've combined like terms, giving us 9x squared plus 6x plus 7. Composite functions don't have to follow an alphabetical ordering or arrangement. Let's take a look at a second example here, a little bit below the halfway down point on the screen. We have f or g of f of x. It can either be written as g of f like that, or g of f using that tiny letter O. In either case, what this is saying is first copy down the function g. Well, that's 3x plus 1. And where the x would go in the equation, I put a set of open parentheses. And inside of those parentheses, I'm going to substitute whatever f of x is. Well, that's x squared plus 6. At this point, all I'm going to do is simplify things. And to simplify things, I'm first going to distribute and have this 3x squared. And then the 3 times 6 is 18 plus 1. Combining like terms will give me 3x squared plus 19. Okay, so there's the final solution for that one. Let's take a look at another example. Okay. Tell you what, you're given f of x equals 2x plus 5, g of x equals x squared plus 4x minus 2, and h of x equals the square root of 6x plus 11. Just to kind of get you warmed up here and give you a chance to try your hand at this, pause the video and solve this first of the two problems. Okay, so hopefully you actually tried this. Notice this is g of h of x. So what that means is I'm first going to copy down whatever g is. Well, that's x squared. I'll leave that open. Plus 4 times x. Need some space to plug in whatever is going to happen for x. Minus 2. Because this is g of h, that means that each of the locations where an x was, I'm going to substitute in this h equation where the x was. So we're going to have here is a square root of 6x plus 11. And we're going to substitute in that exact same thing, 6x plus 11 there. At this point, I'm going to go through and do the algebraic simplification that's appropriate. If I square a square root, that gives us 6x plus 11. The second term is just 4 times the square root. That will not simplify. So I'm left with the square root of 6x plus 11, and there's a minus 2. We can combine the 11 and the minus 2. When we do that, we wind up with the equation 6x plus 9, remember 11 minus 2, plus 4 times the square root of 6x plus 11. And there's that one done. Okay, pause the video and try doing this second problem. Hopefully actually pause the video. Let's see what happens here. To solve this one, it says first copy down g. Well, g is going to be x squared plus 4 times x, and I'm going to put empty parentheses there, minus 2. Then, in this case, the notation says we're going to plug whatever f is into those spaces where the x was in the original equation g. So that means I'm going to substitute in a 2x plus 5 here and a 2x plus 5 here as well. Okay, after that, it's all just algebra. First, I'm going to FOIL this out, which will be a 4x squared plus 20x plus 25. Then from this second term, I'm going to distribute the 4, which is going to give us 8x plus 20 minus 2. Combining like terms, we have our 4x squared. We have a 20x and 8x, which is going to give us plus 28x. Then the 25 minus 2 is going to be plus 23. And there is the result of that composite function. Okay, where does this composite stuff come into play anyway to use a chain rule? Well, what the chain rule is, a chain rule is a way to compute the derivative of a composite function, one function inside of another. When you do the derivative of the one function inside of the other, let's see if I can make this a little bit bigger maybe. Hopefully a little easier to read. The pattern for computing the derivative is f prime of g of x times g prime of x. That may or may not make much sense to you. If it doesn't, that's fine. We're going to go ahead and work through a couple of these. The first one we're going to work through here is the square root of x squared minus 7x, and we're going to compute the derivative with respect to x. Before I start applying the chain rule, I'm going to first write the square root, in other words, replace the radical sign with a rational exponent. which is going to give us x squared minus 7x to the 1/2 power. Okay, so how do we now work on this? I liken this to unwrapping a present. When you unwrap a present, the first thing you do is you deal with the stuff on the outside, the wrapping paper and the ribbon. The stuff inside, the gift itself, is left unchanged. What I'm going to do first is I'm going to look at the outside part. Well, that's this square root stuff. I'm going to take the derivative of just the outside part. Well, that works like a power rule. If I have something to the 1/2 power, the coefficient becomes 1/2, and the exponent is reduced by 1. So I'm going to have now a coefficient of 1/2, a new exponent of a negative 1/2, and notice, really important, the stuff inside is not changed. Just like when you're unwrapping a gift, when you're removing the wrapping paper, you're not dealing with what's inside. Same thing here. The x squared minus 7x is on the inside. We're not going to deal with that while we're dealing with the wrapping paper. All right, so at this point, we have dealt with the outside part of the function. Then, as with the gift, once you get the wrapping paper off, you open the box or whatever it is, and you actually access the gift. Well, the second part of the chain rule says, hey, the stuff inside needs to have a derivative applied to it as well. The derivative of the x squared is 2x. The derivative of the minus 7x is minus 7. And this whole thing, this entire length, is the derivative. Let's take a look at another example. Here we have a situation where we have x cubed plus 11x raised to the 15th power. One way to solve this would be to multiply it out 15 times, combine like terms, and then use the power rule. Yeah, that sounds like a lot of fun. Let's not. Another way to look at this is there is a function on the inside, the x cubed plus the 11x, and on the outside is another function, an exponent of 15, applied to what's inside. We can use the chain rule here. When I apply the chain rule, I'm going to use that same mindset of unwrapping a gift. I'm only going to deal with what's on the outside. I'm going to leave the stuff on the inside alone. So it might be a safe way to do this first step is to just write down the x cubed plus the 11x, put parentheses around it. That way you don't mess it up. Then what I'm going to do is with this exponent, I'm going to bring it out front as a coefficient. See it right there? There it is as a coefficient. Then I'm going to reduce the exponent by 1, and we have a 14 in the exponent, a coefficient of 15 in the front. We've dealt with the outer function. We now need to compute the derivative of the inside. Well, the derivative of x cubed plus 11x is 3x squared plus 11. So we have first, this is f prime of the g of x. We've taken the derivative of the outside, left the inside alone, and this part here is the derivative of the inside. So you can see we actually have followed the pattern for the chain rule. Let's take a look at something like this. Yeah, this is a little messier. We have a cube root, we have stuff in the denominator. Yeah, there's all kinds of stuff going on here. But the good news is, back in the review section R.6, if I recall correctly, we were working with rational exponents and rewriting rational functions using rational exponents. So this can be rewritten like that. Okay, the 3, the coefficient remains there. Now, notice this is a cube root and a square. So we have here the square, the 2, the cube root, the 3, and then there's a negative on that exponent because it was originally in the denominator. And we apply that exponent to the 7x minus 14. To compute the derivative of this now, we're just going to bring the 3 along. The 3 is the coefficient, just comes along for the ride, if you would. The rest of this, I need to use the chain rule on. First, I'm going to do the outside part, leaving the 7x minus 14 alone. In the process of leaving the 7x minus 14 alone, I'm just going to write that down. Then what I'm going to do is I'm going to take this exponent, bring it out front. Aha, there it is. It's now a coefficient. Then I'm going to subtract 1 from the exponent. And when I subtract 1, I get a minus 5/3. Okay, all kinds of good stuff going on there. The next thing that happens is to now take the derivative of the inside. Well, the derivative of 7x minus 14 is 7. In this case, it would make some sense to try and clean this up a little bit. Notice we have a couple 3's here that'll cancel. We have a 7 times the negative 2, which will give us a negative 14. Then we have our 7x minus 14 to the negative 5/3, and that finishes that one off. All right, let's take a look at something like this one. Notice here that we have something times something else. That means we got a product. That means we need to first use the product rule. Oh, the product rule. You should remember that. That's this f prime g plus fg prime. Okay, so when I go to take the derivative of this, I first need to take the derivative of f, the first part. Here's f, here's g. But notice when I go to take the derivative of f, that requires a chain rule. Wait a minute. There's a chain rule inside of the product rule? Yep, it can happen. And in fact, here it is. It's not that uncommon of a thing to have happen. So what I'm going to do is I'm going to take the derivative, applying the chain rule. First, the exponent of 3 will be brought out front as a coefficient of 3. Whatever's on the inside, this x squared plus the 8x, remains unchanged on the inside, and the exponent is reduced by 1 from 3 to 2. Okay, so that has f prime. Now, as I continue on my product rule, the next thing I need to do is to include a factor of g. That's this x cubed minus 5x. So write that down, and we're moving right along here with this. Okay, product rule then says plus. So I'm going to remember to include my plus. Then the next term in the product rule, or factor, is f of x. Well, that's this x squared plus 8x cubed. Good. And the last factor right here is where I took this, computed a derivative. The derivative of x cubed minus 5x is 3x squared minus 5, and there you have it. Okay, so at this point, we now have the derivative, and notice it required 2 steps. A first step where we identified this as a product rule, and a second step where we applied the chain rule as it was needed in the product rule. Okay, at the very bottom of the screen is a similar problem. Pause the video and work through this. Okay, hopefully you actually paused the video and got as far as you could. You might have gotten stuck, that's fine. Hopefully the first thing you noticed was, hey, this is going to require a product rule just like the previous one did. This first factor here I'm going to label F, and this second factor I'm going to label as G to provide some guidance as I'm doing the product rule, which is outlined for us at the bottom of the screen. To compute F prime, I need to use the chain rule on this. When I apply the chain rule, I'm going to have a coefficient of 4 where the exponent comes out front. I'm going to include my 5x plus 2, just write it down without changing anything. Parentheses, then I'm going to introduce the exponent reduced by 1, which is going to give us this exponent of 3. Now be careful, because it's kind of like a situation where you're given a gift and you have unwrapped it, but until you take it out of the box, you've not really completely received the gift. We've dealt with the exponent of 4. Now we need to deal with the inside. The derivative of the inside, the derivative of 5x plus 2, results in that 5 that's sitting there. Following along on the product rule, the next factor that goes in is just copy down g. That's x squared minus 8x, that whole thing raised to the 7th power, plus, oh yeah, that's in the product rule. Then the next factor is f. Copy down the 5x plus 2 to the 4th power. Got that. And the very last factor in this is going to be the derivative of g. Well, this is going to be a situation where we're going to apply the chain rule again. We're going to bring the exponent of 7 out front as a coefficient, leave the expression on the inside, the x squared minus 8x alone, and then reduce the exponent by 1 to 6. That's the outside part of the chain rule. After that, we then need to do the inside part of the chain rule, which says take the derivative of the x squared minus 8x, and that derivative gives us 2x minus 8. You may need to play through these a couple of times. This is a rather complicated process. Complicated in that there are a lot of steps to it. Once you get the hang of the steps, you just keep doing these same steps over and over as needed to work through to a final solution. Let's take a look at something like this. Here we have a function on the inside and raised to the 7th power on the outside. So the outside function is going to be raising this to the 7th power, and the inside function is going to be this x squared plus the 5 plus 2x to the 4th. All of that stuff's on the inside. When we apply the chain rule, because we have an outside function and an inside function, I'm first going to take the exponent of 7, put it down as a coefficient. Then I'm going to copy everything that's on the inside without changing it in the least. There it all is. And apply an exponent that is 1 power less than what we had before. So 7 minus 1 is going to give me the 6. Okay, so that's got that taken care of. The next thing we need to do is to take the derivative of the inside part. Now be mindful that the inside part is just what's in the orange box. Part of this is real straightforward to do. The derivative of x squared is 2x. Plus, we now need to take the derivative of this 5 plus 2x raised to the 4th power. Well, that's going to require a chain rule again. Okay, so if I'm just looking at the 5 plus 2x to the 4th power, I'm going to bring the exponent out front as a coefficient. I'm going to leave what is inside, the expression inside, alone, and then I'm going to reduce the exponent by 1. That is the equivalent of unwrapping the gift, removing the wrapping paper. After we've done that, remember we've just taken the derivative of the outside of this function. The next thing we need to do is to take the derivative of the inside of this function, which gives us a 2. At this point, I would just leave that alone. There's not a whole lot you can do here to clean this up. About the only thing you could do if you really wanted to is you could take this 2 times that 4, and then you would have 2x plus 8 times the 5 plus 2x cubed. Otherwise, that's pretty well what you've got. Okay, Let's take a look at one last problem here. You're asked to compute the equation of the line tangent to y equals the square root of x squared plus 3x at the location 1, 2. Okay. Now, I wouldn't necessarily have to give you this. I could have put x equals 1, in which case the y value would have been the square root of 1 squared plus 3 times 1, which is the square root of 4, which is, oh, look at there. So realize I don't necessarily have to give you the y value, or you don't necessarily have to be given the y value wherever it comes up. Just substitute x into the function and you're good to go. Okay, to create the equation of a tangent line, we're going to use the equation of a line y equals mx plus b. I always kind of like to write that down because it helps to set things up for me. I know I need to compute one, a slope, and secondly, I need to compute the y-intercept, that b value. So I need to compute m in my function and b in this function, or tangent line, whichever you all reference it as. To compute the slope, slopes are derivatives. Derivatives are slopes. Okay, I'm going to try and say that in every video from this point out when we're dealing with derivatives to remind you that a derivative is a slope. It talks about how is the y changing with respect to how is the x changing. Okay, to get the slope, I first need to take my function. I'm going to rewrite this as x squared plus 3x raised to the 1/2 power. We have a square root applied to a polynomial. That's a chain rule. You have a function inside of a function. To compute the derivative, I'm going to take this exponent and it's going to become my new coefficient out front. I'm going to use the inside part, this x squared plus 3x, just bring that down. And then I'm going to reduce the exponent by 1. A half minus 1 is a negative 1/2. Okay, so there we've done part of the chain rule. What we need to then do is to take the derivative of the inside part. Well, that's going to give us 2x plus 3. We want to evaluate this at x equal to 1. Remember, that's the point in the upper right-hand corner of the screen. That's the point we're working with. I'm going to substitute 1 in for x into this derivative. And I'm also going to rewrite this so hopefully it looks a little friendlier for you. I'm going to have 1 over 2. I know that this x squared plus 3x goes in the denominator because the exponent is negative. And since it's a negative 1/2, it's going to be a square root of x squared plus 3x. But in place of x, every place there's an x, I'm putting 1. So it's going to be 1 squared plus 3 times 1. The second part is going to be 2 times x. Well, x is still going to be 1 plus 3. Simplifying this, we wind up with the slope has value of 5/4. Ta-da! There it is. To compute the value of b, the y-intercept, I'm going to take the slope that I know, 5/4, substitute it into y equals mx plus b. I'm going to take the x value of 1 that I'm working with, as well as the y value of 2, substitute those in as well. And what that leaves me with then is this equation right here. I'm going to have 2 is equal to 5/4 times 1 plus b. Solving for b, you get b is equal to 3/4. Okay, so I have a slope and I have a y-intercept. This allows me to then write the equation of the tangent line, y equals m, 5/4 x plus b, 3/4. And that's how you work out the equation of the line tangent to a function where you need to use the chain rule. Be patient with yourself. These take a little bit of time. You may want to work back through these problems a second or third time on the video. I hope this is helpful.